Hello, I'm Eric here. In this project, I'm gonna show you the server for Node.js as an additional version of the ESP32 walkie-talkie project. All ESP32 TTGO devices become clients, or the server works separately. The sound you are hearing is from the I2S microphone from the one of the ESP32 clients, not from video recording. Now the local server is running through my MacBook, and I made it possible to listen to the audio data of the clients directly to my MacBook speaker. I can say my words well because of the feedback sound from my MacBook. Anyway, we are getting voice data correctly. Also, I love this sound quality. Okay, let's get started. By configuring a system like this, you can configure more diverse communications. You can also configure this server to increase the number of the clients that can connect at the same time. This may vary depending on the hardware performance and network bandwidth. In this video, I only deal with local server configurations, but if you deploy this server outside like AWS, Microsoft Azure, or Google Cloud Platform, you will have a system that can be accessed in an internet-enabled environment. That will be quite interesting. As you can see on the right, all the devices connected to the local wireless network. My MacBook is connected to a wireless router and it works as a server. Also, ESP32 client devices connected to the same wireless router. The client for ESP32 is the same as the previous project. You can get the source code from the previous video. Let's talk about the server created with Node.js. The Node.js server is very similar to the server code for ESP32. It has almost the same logic. So only what I did for the client side is change the host IP address. That's all, and you can do it, right? I will explain only other parts of the existing logic from the previous project. First, you can see the speaker part here. A typical server doesn't have any outputs like a speaker. In my case, I added this part for testing because the server works on my Mac. Output PCM audio data from the I2S microphone on ESP32 client to the speaker in the server. Here's the same as the default I2S settings from my ESP32. The bit depth is 32 bits, one channel, the sampling rate is 16K Hz. I made it output to the speaker through a function called buffer rate. The WebSocket server starts here. Like the ESP32 server in the previous project, the port name is the same. Here are the WebSocket server settings. Only the required parts added. The number of concurrent clients is 10, and if the packet size is below 1024 bytes, it's not be compressed. When the client is connected, it sends the current timestamp to the client side. We cannot send the timestamp of the milliseconds because the unsigned long type allows up to 10 digits. You can simply divide by 1000 and send the timestamp of seconds, but I don't like this method because the interval is 1 second in this case. So I got the last 8 digits and made them send. Each unique ID was assigned because it's necessary to allow multiple client connections. It's created with a combination of the timestamp and a random string. And then making the state of the connected client idle, the default setting is up to here. One thing I almost forgot is a timer of 5-second intervals is activated to ensure that the connected client is still connected. When the last message or ping received exceeds 10 seconds, it determines that it's disconnected and disconnects. This part is the processed messages received from the client. The first thing to do is to update the timestamp of the client. You can easily distinguish content types on WebSocket. In my case, the text is used for simple message forwarding and binary is PCM audio data. When text is received from one client, it checks the states of all connected clients. It gives permission to speak only when all clients are idle. That way, the client will receive the timestamp is sent again and will be able to transfer binary data which is from the microphone. Or other clients now have to become listening mode. So the command is issued because it sends a timestamp. The client in speaking mode continues to send binary data, and the server that received it sends it to the connected other client. This is the role of this server. All data passes through the server. So we can use the PCM speaker module to hear what audio data is coming and going. The transmitted data is PCM data, so you can listen to it through the speakers without any modifications. However, there are some bugs in macOS, but there is no problem with working. Not sure, but there will be no problem with other operating systems. Just try if you need this part. My code and explanation are up to here. In the basic concept of the previous project, it's created Node.js server that support multi-clients. The link to the source code can be found in the description below. Please leave your questions or any ideas for this project below this video. Okay, let's see the result. One, two, three, four, five. All sounds you hear is from ESP32 client, not from video recording. This is Eric. Can you hear me? The sound quality is much better than the small speaker. All works good, right? There is a lot of warning messages from the core audio from macOS. If you are using Windows OS or Linux, it's gonna be fine. I hope it will be fixed in the next version of the audio speaker library. How was this project? Was this good? I hope it really helped your project based on my projects. I'll be back with more interesting projects. Thanks for watching. See you in the next project.